Hi everybody. In this video we're going to talk about scattering of light. And who I have on the cover here on the title page is Lord Rayleigh. So we're going to look at Rayleigh scattering. Of course his real name was John William Strutt. He became Lord Rayleigh after his father, who was Lord Rayleigh, passed away. He was an interesting guy. He, of course, was Lord. He became director of the Cavendish Laboratory after Maxwell died. He took over from him. He was Chancellor of Cambridge University. He was the Justice of the Peace, and among other things, a very good scientist who won the Nobel Prize in 1904. And he won it for measuring the densities of the important gases that were known at the time, and he discovered argon. So, a well-known scientist. So, yeah, we're going to talk about scattering of light. You've already talked about one type of scattering, and it's called Compton scattering, and it's when light scatters off of basically free electrons. Of course, Compton, when he did this work, he didn't use free electrons. He used, I think, electrons around gold, but the valence electrons in the gold atom can really be considered to be free, especially when you hit them with high energy X-rays. So you've already talked about that, and you found that the photon wavelength does change, so the photon energy does change with that. But we're going to talk about Rayleigh scattering, and in that case the photon energy does not change. And let me move my picture down to here. We'll also talk about my scattering, where again the photon energy does not change. Rayleigh scattering and my scattering are prevalent in our atmosphere. This is mostly what the scattering that goes on around us is. Then there is something called Raman scattering. In this case, the photon energy does change. Raman scattering is used to study, for example, the rotational and vibrational energy of molecules. Then we'll talk about fluorescence and its closely related cousin, phosphorescence. So we'll mention all of those things. Okay, let's talk about Rayleigh scattering first. So what happens? This is when light is scattered from very small particles. And when it occurs, so you have your incoming photon, here's your small particle, and with all this scattering, light somehow kind of gets absorbed by the atom, molecule, dust grain, whatever it is, and re-emitted. So in this case, it could come out this way, the re-emitted light, the scattered light could come out this way, it could come out this way. It can come out in all directions equally probable. So scattered in all directions equally probable. The wavelength, the incoming energy of the incoming photon is HF, and so is the outgoing, the scattered. There is no change. This kind of scattering explains the blueness of our atmosphere. I should also add into this that Rayleigh scattering occurs, it's more prevalent for shorter wavelength light than longer wavelength light. So the violet is around 400 nanometers, and the red around 700 nanometers. So the shorter wavelength stuff rarely scatters more prevalently, more easily, and so we see, since it scatters in all directions, it looks like the shorter wavelength, the bluer light, comes from all directions. And that's why the sky looks blue to us. There's another type of scattering that occurs in the atmosphere called my scattering. And this occurs for larger particles like water molecules or water droplets. Or dust grains. Now, with this type of scattering, there is a preferred direction for the scattered light. So here's our incoming, our incident. I guess I could put a little I for our incident. Light hits our dust particle, water droplet. Now, you get more light, and I'll indicate that by a larger arrow. You get more light out in this direction and less in this direction. So my length of my arrows don't represent a different wavelength or anything. If they're longer, it's just that you're going to get more scattered light out in this direction. But it's still the same energy. You don't change the energy. So when the energy of the scattered light is equal to the energy of the incident light, we call that elastic scattering. So energy of scattered light equals energy of incident light. We call that elastic scattering. Okay, so let's take a little break from talking about the scattering and say what is actually going on in the scattering process. Okay, we have an incident light, and I already told you that in some way that light's getting absorbed and then re-emitted. So let's talk about that for a minute. So this represents our incident light coming in with some energy. Now, you guys know, let's say we have our electron down here in the, let's say this is the ground state. Now, we learned that for the atom to absorb that photon coming in, we have to have an energy state up here so that the energy difference is exactly equal to the energy of the photon, and then we can get that electron making that transition up. But not all dust grains, water molecules, and that have an infinite number of states so that you have exactly the energy you need for various incoming photons. So what actually is happening? So what actually happens is that incident photon has an electromagnetic field that is shaking that electron. So that electron actually can go from the ground state, raise up to some other energy state, even though there is not an energy state up there that satisfies the energy eigenvalue equation. okay? It can go up to whatever state is needed if it doesn't stay up there very long, if it obeys the Heisenberg uncertainty principle. So it can go up a certain amount of energy, can only exist for a certain amount of time. So we call the state that it actually goes up to a virtual state. And it's virtual because it's not this energy. If this is energy up here, this energy is not an eigenvalue for the energy eigenvalue equation. So since it's not a state that actually satisfies our energy eigenvalue equation, but we think the electron goes up to that, but comes right back down because it can only exist up there for a very short time, then we call that a virtual state. So what's happening here is we have this photon comes down, whether or not there's an energy eigenvalue the right energy or not, we get a transition of that electron and rapidly can come back. Okay. So what's happening with the Rayleigh scattering is it goes up, comes back, and then we get our emitted photon off in any direction. So we would have our incident light for Rayleigh. This is for Rayleigh scattering. Our incident light, certain energy HF. Here's our electron in the ground state. Goes up to the virtual state. And then very quickly makes the transition back down, emitting a photon with the same energy. Okay, so let's talk about scattering that the wavelength or the energy of the photon does change. So let's talk about Raman scattering. And I mentioned we use Raman scattering to study the vibrational and rotational energies. Of molecules. When we do that, we use a monochromatic light. We use laser light as our incident light source. So what happens here is you have your incident photon with a certain energy coming in. Your electron is here in your ground state. The photon shakes up the electron up to allows it to make a transition up to this virtual state. And then there's another state. So it goes up to this high state here, but then it makes a transition, and it might, for some reason, make a transition down to this state rather than this one. Maybe it's more probable to go down to this state. So you get a different wavelength, different frequency, different energy, a shorter energy. So if the scattered light HF is less than HF prime, the scattered energy is less than the incident energy, we call this a Stokes Raman scattering. And if it goes the other way, if you have your incident photon, your electron in the ground state going up to the virtual, making this transition, and then it goes down to a state that's farther down here. So you notice I didn't call this the ground state now. Call it an initial state. That's probably what I should have called it here, but we get our electron makes the transition up and then goes down here. So HF prime, in this case, HF prime is greater than HF. So this is called anti-Stokes. So how can this kind of thing occur? It could be that you have in a molecule, maybe you have rotational states, and then you have some other electronic state up here. So basically you have an electronic state, you have your rotational values, and maybe you have another electronic state up here, and you have an electron right here. It makes a transition up and then makes a transition down to a different rotational state. So this is supposed to represent the rotational states. These are the electronic electronic states. Like when you had the hydrogen atom, you had n equals 1 electronic state, n equals 2, n equals 3, and so forth. Okay? So, yeah, we use Raman spectroscopy to study rotational vibrational energies of molecules. Okay. So then the last thing I want to mention to you is fluorescence and phosphorescence and the difference between those two phenomena. Okay, so let's first talk about fluorescence. That's a U. So fluorescence, what's going on here? So we have our incident photon and energy HF. So what happens in fluorescence is we have a coupled pair of electrons in a lower energy state. Coupled pair means one has spin up and one has spin down. It comes in and it allows one of these to go up to a higher level excited state. So this is not a virtual state, this is some excited state that the electron, let's say, can go up to. And then what happens is, then you take this and you have maybe a collision with another molecule. There's a non-radiative transition. Somehow this molecule gives up a little energy. So you get a non-radiative transition. And then down to this electron, which had spin up in this case, is now here with spin up. Then this will make a transition back down to the initial state down here. So it's moved back down here and emits a photon in this transition, HF prime. So the energy of this photon is less than. So you might take something with infrared light and shine it and make this phenomena happen, and what comes out is a longer wavelength. So maybe, a green light comes out. The time for this to happen is on the order of 10 to, very fast, 10 to the -4 to 10 to the -8 seconds. But in the end, you get a photon that's got a longer wavelength. So how is that different than phosphorescence? So phosphorescence again, you start with coupled electrons. You have your incident photon with energy HF coming in. Allows one of these to make a transition. So let's say this one makes the transition up to an excited state. So very much the same. But what happens is, in some cases, you can get a flip of the electron spin. So now these are no longer a coupled pair. They have the same spin, okay? And then we can have a transition down to a lower state again. So it makes an easy transition down to here. But now, because it's flipped its spin, it doesn't want to go down back to this ground state. So it kind of wants to hang out here for a while. We call this a metastable state, but eventually it will make the transition down and we'll get a photon out. And again, a longer wavelength, less energy. But this can happen, the time it takes for this to make this transition from this metastable state back down to the ground state can be on the order of seconds. So times on the order of. So that's the difference between phosphorescence and fluorescence. This happens very fast. This can take a long time. So if you've ever, excited a phosphorescent screen, it takes a while for it to come back down so it's not glowing anymore. Or fluorescence, that'll happen. You turn off a fluorescent bulb and right away, you lose the light. So that's the difference between fluorescence and phosphorescence. So, please contact me if you have more questions. That's what all I'm gonna say about scattering of light right now. And then we'll go and talk about vibrational energies of molecules and then put everything together.